In Houdini, there are two ways to store volumes. There's the Houdini created way called volume, and then there are also VDBs. Both of them are ways to store voxels, so let's actually begin there. What is a voxel? If you have an image is a rectangle made up of pixels. If you zoom in close enough, you can see an image is made up of just these tiny little squares. Each one of these squares is called a pixel, and in the case of images, each pixel stores a color. When you have enough pixels, you get a really nice smooth-looking image. Voxels are three-dimensional pixels. So if you have a volume and you want to fill the volume with tiny little cubes, each of those little cubes is called a voxel. And while pixels and images store color, voxels and volumes can store any data you want. They can store color. They can also store just a number. They can also store a vector if you want to use a volume to represent like wind or other forces. So let's take and explore VDBs a little bit more. VDBs weren't created by Houdini. They were actually created by DreamWorks Animation. And you can learn all about VDB by visiting the website openvdb.org. It's called OpenVDB because it's an open source project. And in the upper left, you can see the logo is a red infinity symbol with OpenVDB underneath. In Houdini, if you make a geometry node and jump inside and press tab, there is a submenu called VDB. And these Houdini nodes all use the same logo, a red infinity with VDB underneath. Returning to the website, we see that VDB actually won an Academy Award, so congratulations. And it's constantly updated. And if you look at the About page, it goes into some of the technical details about how it was developed and why it was developed. The VDBs really shine when dealing with sparse volumes for things like fog or smoke or what have you. When I first was studying VDBs, I kind of wondered what VDB stood for. I guessed it was for volume database. That was my guess, and I could not have been more wrong. It actually stands for volumetric dynamic grid that shares several characteristics with B+ trees. Suffice it to say, it's a lot more technical of an acronym than I expected. So let's go ahead and create our first VDB in Houdini. And before we begin, let's just give us as much room as possible. And since we're going to be working with volumes and not geometries, we won't need any of these geometry tools. We'll start by using the rubber toy that comes with Houdini. If you click the node info node, you can see that this geometry is made up of 12,874 points and a lot of primitives and polygons. Let's convert this to a volume, and we're going to do that by using the VDB from Polygon node. If we highlight that, the blue rubber toy now looks blocky. These gray blocks are voxels. And this looks like a poor approximation for the rubber toy. And if you click the info node, you can see that this VDB, which is called surface, only has 4,481 voxels. To put that in perspective, a typical frame of HD video is like 1920 by 1080, roughly 2000 by 1000 or 2 million pixels. So this is way too few voxels to get something that looks nice. So let's make each voxel a lot smaller. Instead of 0.1, 0.01 in size. That now looks like a rubber toy. We'd have to get really close before you'd start to see some blockiness showing up, but it is there. And if you wanted to, you could make the voxels even smaller. But when the voxels are cubes of 0.01 in size, we're now working with 443,779 voxels. Let's go ahead and see what happens if we go 0.01. It's calculating there. That looks a lot smoother. But we're now using 43 million voxels. And unless you're doing a final render, it's probably best to keep your voxel size reasonably small. Now, the VDB from Polygon node has two options down here. What type of VDB do you want? Do you want a distance VDB or a fog VDB? The distance VDB, what that actually does is it creates a shell of voxels on the outside of the geometry. And you can see that it's a shell by zooming in. Once we pass through the skin, we are now inside the rubber toy. That's one of the legs. Here's another one of the legs. And if we turn around, we should be able to see the neck of this rubber toy and find out and see the head. So where is the head? I think there it is. I think that would take us into the head of this rubber toy. The point being, this is a hollow volume. If you want a solid volume, you would create a fog VDB. Now this fills the geometry with voxels, but it treats the voxels as a fog. So the values stored in the voxels gradually ramp up from 0 outside of the shape and gets into a little higher and higher range until you get into the center of the shape. That's why it has this appearance that you can kind of see through it. And if you click on I, you can see this does indeed have more voxels, about 900,000 voxels in a fog versus a distance VDB is about 443,000 voxels. So let's work with the fog. You can see the box containing the shape. That's called the bounding box. And to make this a little easier to see, let's hit D, bring up the display options, go to the background and make it dark. And we are also going to turn off this grid. Okay, that's a lot easier to see now. The fog VDB is currently named density. Let's just rename it to foggy, because you can call it anything you like. Next, what I'd like to do is explore this volume using Python. So let's come up and add a new Python shell pane. Let's collapse this parameters pane. Let's give ourselves a little more room in the Python shell. Also, before we go crazy with Python, let's come back to our network. Here we have the rubber toy. We converted it to volumes. Let's go ahead and add a null node and let that be our output. That way we can get references to the output, and later on if we want to insert other nodes, we don't have to change any of our Python code. The first thing I'd like to do is to get a reference to the output node. From the output node, we can then get the geometry. From the geometry, we can get the VDB, and then we can use a lot of functions to explore the voxels inside this volume. To get the output node, we're going to use the Houdini Python module, and there's a node method, and you type in the path to the node you want. We're going to start with the object context, the geometry node, and the output node that we added. And now we have the output node. Now each surface node has a geometry attached to it. So let's call the geometry method to get the geometry object attached to that node. Now the geometry has a lot of points. It has a lot of primitives and vertices and other things. We're interested in the primitives because VDBs are primitives. And you can see there's just one. We've only created one VDB. So let's go ahead and get that, and we'll call it VDB. So we're going to take and get all the primitives, and we just want the first one. And we do that using parentheses are for calling functions, brackets are for accessing, entries inside a list. The list of primitives only contains a single primitive, and we start counting at 0. So by using bracket 0, we're able to get the VDB. Now, if you just type in VDB, you can see a little summary of what this object is. It's a VDB object. It is a primitive number 0 in the geometry that's attached to this node. So what functions are available to us? In Python, if you type in dir, that's short for directory, and it'll give you a list of methods for this object. So let's type in the directory for VDB, and there we go. There's quite a few methods that we can call. I'd like to explore some of these. The first one is, let's take VDB and call the resolution method. If you type the open parentheses, you can see that this is going to return the dimensions of the bounding box in voxels. And it shows us that it's 203 by 165 by 182 voxels. You can see these by coming to the output node, clicking the info, and that's what's displayed here. It's for the foggy VDB, the size of this volume in voxels is 203 by 165 by 182. Next, we can see how many voxels are actually being used. So that's how many voxels will fit inside the bounding box, but some of them are black. We want to know how many voxels were used to make the rubber toy volume. To find that out, you call the active voxel count method. So we're using 897,498 voxels. Now, how many voxels can fit inside the cube? To find that out, you would multiply 203 by 165 by 182. which is a little over 6 million voxels. So this box could contain 6 million voxels, but the rubber toy only used about 900,000 voxels. A few other methods I'd like to point out to you are POS to index. That's position to index. And for that, if you type in position to index, you type in an XYZ coordinate for a point in space, and it will give you the index numbers for the voxel. So for example, what is the indices for the voxel at the origin? 0, 0, 0. So that's a little boring, but what if you go 1, 0, 0.5? Then the index of that voxel is 100.05. And you can also reverse the process. If you have the index and want to find out the location, you can use the index to position method. And here, if we pass in the index 100.050, it does give us the position 10.05. So next, I'd actually like to get the value of a voxel. Here, for the position 10.05, this is the index for that voxel. And to find the value for that particular voxel, you call the voxel method, and you pass in the index, not the position. You pass in the index. And that has a value of 0. So that's interesting. And that kind of makes sense here. If we look at it sideways, the center is black. Well, how about this? Let's find the voxel for, we don't quite know the index, so we're going to use the position to index method. And let's say we want x to be 0, y to be 0, and z to be negative. How about 0.5 actually? Positive 0.5. So, made a mistake. The way I called the position to index. When you call the position to index, they want you to pass in the position as a tuple. And I didn't do that. So sorry about that. But I will not edit out my errors. So we're going to pass in a tuple representing the position of the voxel we're interested in. And if we look at the volume from the front, this is x equals 0, y equals 0. And from the side, this would be z maybe about 0.5. So that's how I chose those. There should be a voxel there, I'm guessing. 0, 0, 0.5. That will give us the index, and the voxel value there is 1. Now, this has 6 million voxels, and we wouldn't go through voxel by voxel to look at it. And they give you a method for looking at a whole bunch of voxels at once, and that's the voxel range method. So we can do voxel range, and here they want you to pass in a box, and it will return the voxel values for every voxel inside that box. Well, this shape, we can actually get the box that it's contained in by using the active voxel bounding box. If we do that, we're going to have to wait as it calculates a little error. I guess it's a little unhappy with me. I should have enough memory to pull this off. Let's see. There we go. There are the values in all 6 million voxels. And you'll notice there are a lot of zeros. That's because of the 6 million voxels available inside the bounding box. Most of them are empty. But if you scroll up, we do start to see some non-empty voxels. So what I would like to do is, rather than display that, let's store all the values in a variable called values. So we now have, if you look at the length of values, we do indeed have all 6 million plus values for each voxel inside this bounding box. Let's count how many of them are 0. To do that, you can take the tuple and call count, and let's see how many zeros are there. There's 5,198,592. Well, for the VDB, how many active voxels are there? It says there's 897,498. And also for this VDB, what's the resolution? It's 203 by 165 by 182. So I want to show you how these relate to one another. If the resolution is 203, 165, 182, that means this box can contain a total of 6,096,090 voxels. This is how many inactive voxels there are. This is how many active voxels there are. So if we add these two together, we should get 6 million. Let's take and add the number of inactive voxels. Those are voxels with a value of 0. And add to it the number of active voxels. And it does come out. So we have accounted for all the voxels inside this box. the active ones, which make this little foggy shape, and the inactive one, which is the empty space around it. So next time we'll go a little bit deeper with VDBs and voxels. Thank you.